Welcome all for the session Registers and Counters. Third unit of Digital Electronics, third semester Electronics and Communication Engineering. In previous sessions, we have learnt about synchronous counter, asynchronous counters, modulus of a counter, mod 5 counters and mod 10 counters, merits and demerits of those counters. Today I am going to present comparison between synchronous and asynchronous counter, configuration of IC 7490 as a decade counter, list of counter ICs available in the market for the development of any product or project, applications of counter where we find in day-to-day life. At the end, we'll have one small multiple choice questions quiz. At the end of this session, you will be going to learn differentiate synchronous and asynchronous counter, configuration of IC 7490 as a decade counter, identify the areas of applications of counter. Now let us study the comparison between synchronous and asynchronous counter. In synchronous counter, what we have studied, the clock pulse is applied simultaneously to all the flip-flops which are present in the counter. That means the clock is parallelly applied to all the flip-flops. Whereas in the asynchronous counter, the clock pulse is applied only to the first flip-flop. Subsequent flip-flops are derived by the previous flip-flops. In synchronous counter, operational frequency is very high because clock is applied at the same time. In asynchronous counter, the operating frequency is less because the subsequent flip-flops has to wait to change the state of the previous flip-flops. Synchronous counters are very faster, asynchronous counters are slower. Cost of the synchronous counter is high due to the design complexity. The cost of the asynchronous counters are low. Synchronous counter design and implementation is complex due to the increasing number of states. Asynchronous counter design as well as implementation is easy compared to the synchronous counter. Large number of logic gates are required for the design in synchronous counter because it requires some additional circuitry what you have seen in synchronous counter design. In asynchronous counter, minimum number of logic gates is required to design the asynchronous counter. These are the few differences between synchronous and asynchronous counter. Whenever we require the faster operation, then we use the synchronous counter. Whenever we require the slower operation, we use the asynchronous counter. For example, measurement of temperature, pressure, etc. does not require any much faster operation, so you can use asynchronous counter. When it is required to calculate any values at the faster rate, then you can use the synchronous counter. Next, move on to the IC 7490. Okay, IC 7490 is a DIP, dual inline package, 14-pin IC, acts as a decade counter. Can be make it as a decade counter. It has 14 pins. Pin number 1 is a input 2. Pin number 14 is a input 1. Pin number 2, 3 and 6, 7 are reset pins. Set and reset pins. And pin number 4, pin number 13 is not used for any function. It is blank. The power supply, that is VCC, will be applied to the pin number 5. The ground is pin number 10. The pin number 12, 8, 9 and 11 are the 4 outputs of the decade counter. So we will study the internal diagram of 7490. This is the internal diagram of 7490. It has 2 counter inside. One is mod 2 counter, another one is mod 5 counter. For clock pulse, we are going to apply at the input A. What you have seen here, input A, that is input 1. Okay, the output of the first mod 2 counter or flip flop A is given to the input to the second flip flop to make it as a mod 10 counter. It is a mod 2 and mod 5. To make it as a mod 10, we have to multiply 2 into 5, nothing but a 10. We have the inputs, reset inputs 1 and 2, set inputs 1 and 2, and VCC and ground. It is required for operation. Here QA, QB, QC, QD are the outputs. And what is the function of these 4 pins? Inputs and outputs. When the reset pins of the inputs is given to the 1, then if both the reset inputs R01 and 02 are logic 1, then all the flip flops will be reset and the output will become 0, 0, 0. If both the reset inputs R9 and R92 are at logic 1, then the counter output is set to decimal 1001. That means binary 1001 means decimal 9. If any one of the pin R01 and R02 and one of the R91, R92 are at low, the counter will be in counting mode. To make 7490 as a decade counter, any one of these 4 pins one from the reset inputs and one from the reset output, it should be connected to the low. Then it will become act as a counter mode. If both the pins, reset pins connected to the 0, it becomes 0. When connected to these 2 pins, reset pins is connected to the 1, it becomes 1001. Any one of the pin is connected both the pins to the 0, then it becomes acts as a decade counter. Now let's study how does it work. This is a connection diagram. That is input A, that is input 1. That is input A, that is input 1. The output of the mod 2 counter is connected to the input to the next subsequent. It is a circuit is like that. Inside this is a one flip flop. Okay, this is a clock. That is input A anta aitala adu. This is a clock. As usual, this is J or K, whatever it is, T. If it is a T input, it is connected to the 1. This is the output is given to the next inputs. This is like this. Inside, there is inside, this is a diagram. This is a clock input to this one. This is output is given here. This is output is given there for the clock here. This is what? QA. This is what? QB. This is what? QC. And this is QD. This is a structure. What is there inside this one? Inside this IC diagram. That is mod 2 means the single flip flop acts as a mod 2. Mod 2 means what? It counts only 0 and 1. Mod 5 means it counts from 0 to 5. Okay, it acts. This is a connection. Just you have to connect the output of the mod 2 counter to the clock input to the mod 5 counter. That is input B. Input A is the clock input to the mod 2 counter and input B is the clock input to the mod 5 counter. This is input B. This is input A. This is only just connection, and the set and reset inputs. Set and reset inputs all are tied to the ground to make it as a counter. Then you have to see the study one by one. How does it works? In mod 2 counter, that is QA, mod 5 counter QB, QC and QD here. When before the application of the clock pulse, automatically all the flip flops are reset to the 0 as usual. That is 0, 0, 0, 0 here. When first clock pulse is applied, automatically this QA is set to 1. That is when first clock pulse is applied, automatically this set to 1. When they set to 1, the QB, QC, QD do not respond because this is a negative edge triggering flip flop. Nothing but a falling edge. Negative edge triggering flip flop. When the transition from 0 to 1, there is no change in the second flip flop. That is B. C. This is D. This is A flip flop. There is no change here. So when clock goes from 0 to 1, the QA changes to 1. There is no change in the QB, QC and QD. When second clock is applied to the input A, here input A, falling edge. When you detected the second falling edge, again this QA goes to the 1 to 0. When it goes to the 1 to 0, when it goes to the 1 to 0, then it becomes a class to the B. Then it changes the state. Then it becomes a 1. Previous state is 0, the new state is 1. Changes here. When it goes to the 1 to 0, the flip-flop B changes, but there is no change in the C and D because it is a transition from 0 to 1. There is no change here. When third clock is applied here, again it changes the state here. When third clock is applied here, changes state from what? 0 to 1. When it goes to the 0 to 1, there is no change at the input B because input B changes only from 1 to 0. So it retains the previous value. What is the previous value? Previous value is 1. There is no change. When the 1 to 1 transition, the C do not change any state and D also there is no change at the D here. When third clock pulse is applied, again the A changes from the state 1 to 0. When fourth clock pulse is applied. When it goes to the 1 to 0, the B flip-flop changes from 1 to 0. The previous state is 1, it changes to the 0 here, 1 to 0. When it goes to the 1 to 0 here, it becomes a clock to the C flip-flop. So C flip-flop, that it changes to state 0 to 1. When it goes to the 0 to 1, it will not become a 0 to 1. It will not act as a clock to the D, so there is no change at the D. Here. When applying the fifth clock pulse, again it changes the toggle state from 0 to 1. When it goes to the 0 to 1, there is no transition at the second flip-flop. There is no transition at the B flip-flop. And when it is 0 to 0 transition, here is also no change at the C flip-flop. When 1 to 1 transition, there is no change at the D flip-flop also. When 6th clock pulse is applied, again it goes to the 1 to 0. When it goes to the 1 to 0, it becomes a clock to the B flip-flop. Again it changes the state from 0 to 1. Previous state is 0, the new state is 1. Again it changes. When it goes to the 0 to 1, there is no change at the C because C changes only from 1 to 0. There is no change here. Again it returns the previous value 1. When 1 to 1 transition, there is no change at the D also. When 7th clock is applied, again it changes the state from 0 to 1. That is QA flip-flop 0 to 1. When it goes to the 0 to 1, there is no change at all here. There is no change at the flip-flop B. And there is no change at the flip-flop C. And also there is no change at the flip-flop D. When 8th clock pulse is applied, again it goes to the 1 to 0, flip-flop A. That is flip-flop means mod 2 counter. When it goes to the 1 to 0, it becomes a clock to the B flip-flop. Again it changes state from 1 to 0. When it goes to the 1 to 0, again it becomes a clock to the C flip-flop. Again it also changes state from 1 to 0. See, when it changes the state from 1 to 0, again it becomes a clock to the D flip-flop because always 1 to 0 is a clock to the next flip-flop. So it also changes the state. It becomes a 1. When 9th clock is applied, it changes the state from 0 to 1. There is no effect to the second flip-flop. Again it returns the previous state 0. When 0 to 0 transition, no effect to the C flip-flop. Again it's 0 to 0. When it's 0 to 0 transition, there is no effect on the D flip-flop. Again it becomes a 1 to 1 transition here. So it becomes 1 0 0. Then now let us study how does it acts as a decade counter. Look at the mod 2 and mod 5 counter in a truth table. The mod 2 counter always changes the states from 0 to 1, 1 to 0, 0 to 1, 1 to 0 for every clock pulse. Because mod 2 means it only 2 states 0 and 1. Here mod 5 counter, see how it responds to the upon the clock from the mod 2 counter. Initially the all are 0 0 0 0. When first clock pulse is applied, it goes to the 0 to 1. Here it is 0. When it goes to the 1 to 0, again it changes states from 0 to 1. Again it goes to the 0 to 1. Again it is 1. When it is 0 0 1 0 1 0 1 0, again 0 0 1 1 1 0 1 1 0 1 0 0 1 1 0 0. That means for every 0, it returns the one value. For 1 also it returns the same, produces the same value. So this modify counter, it counts twice, 2 times of that value, that is 000, 001, 011, 100. It counts 2 times, 000 2 times, 101001 2 times, 011 2 times, 100 2 times. So it multiplies 5 into 2, nothing but a 10 times here. So in this fashion it works as a mod 10 counter. Now let us look at some ICs available for construction of the counters. 74168 is a synchronous 4-bit up or down decade counter. It is up or down decade counter. We can construct either it is a 4-bit up counter or a 4-bit down counter. 74169 again it is synchronous 4-bit up down decade counter. 74190 synchronous up down decade counter. 74191 synchronous up down binary counter. There is a difference between decade counter and binary counter. Means decade counter counts from 0 to 9, binary counter counts from 0 to maximum value. 74192 synchronous up down decade counter with final value. 74193 synchronous up down binary counter with clear. 7468 dual 4-bit decade counter. It has 2 decade counter inside the IC. 69 also 4-bit dual 4-bit binary counter. 7490 what you have studied, decade counter separate divided by 2 and divided by 5 counter. You can make it as a 5 divided by 5 counter or mod 5 counter, or you can use it as a mod 2 counter. 7493 also separate divided by 2 and divided by 8 sections. It has 4-bit binary counter. 74160 synchronous 4-bit decade counter with synchronous asynchronous clear. 74161 synchronous 4-bit binary counter with synchronous clear. These are the ICs available in the market. Then what are the applications of the counter where these counters will be used? Okay, some list. Frequency counters. You might have seen in the labs we are using the signal generator or function generator. Okay, in the digital function generator we can see the frequency of the input signal. So it converts the analog to digital, and digital we are counting the frequencies. Digital clock we have seen in the mobile phone, in the wristwatches or in the wall clock. Time measurement of the time duration between the one state to the next state or one process to the next process. And analog to digital converter, that we will study in the 4th unit. Next, frequency divider circuits. The ultimate goal of this flip-flops is the divided by 2 frequencies, so we can use the frequency divider circuit. Digital triangular waveform generator, that we can see in the 4th chapter. We will study detail about this one. So we will have some descriptive type questions that may come in the examination. You may get in the examination. Demonstrate how to configure 7490 as a decade counter and write its truth table. Compute the overall modulus of cascaded counter, model 5, mod 8 and mod 4, and justify your answer. This question was asked in the previous year examination. That is mod 5, mod 8 and mod 4. Ent is 40, naka nakala 16, naka nakala 160. That is mod 160. Compare synchronous and asynchronous counter, what you have studied, and list the applications of the counter. These are the possible questions you may get in examination. Okay, list the ICs available for counters here. Okay, multiple choice questions. What is the difference between 7490 and 7493? 749 is a mod 10, 7493 is a mod 16. Okay, mod 16, mod 10, mod 10, 12, 16, 10, 20. Okay, what is this one? The difference between the 7490 and 7493 is that 7490 is a mod 10, 7493 is a mod 16 counter. Thus 7490 travels 10 states and 7493 travels 16 states. Then answer is A. Next question, which of the following is decade counter? So we have studied 7490 is a decade counter. The cascaded model of 5, 3 cascaded model of 5 counters have an overall modulus of 3 cascaded model of 5. That is, you have to multiply 3. 5 into 5 into 5. That is 125. 5 into 5 into 5 is equal to 125, because the modulus of the counter, when you cascaded, we have to multiply between the modulus to modulus, section to section, or stage to stage here, which is not an example of the truncated modulus. The answer is A. An n-bit counter whose modulus is less than the maximum possible is called the truncated counter. Here 9, 11 and 15 modulus counters are truncated counters, whereas modulus 8 is the not truncated counter. A counter which counts from the 0 to maximum value is not a truncated counter. Any counter which counts less than its maximum value is always a truncated counter. So that is 2 power 3 is equal to 8. 8 is not a truncated counter. 9, 11, 15 are always a truncated counter. These are the references that we can go through. This is a digital team. Digital electronics team were all contributed to development of this content. Thank you.